Hello class, welcome to lesson 2.5. We're going to basically go over the problem from Canvas on 2.5, which is all on the equations of regression lines. Not calculating them, but just regression lines themselves. So we want to make some predictions and calculate some residuals here. So the first question, we have the equation of the regression line relating the temperature in degrees to the chirps per minute of the cricket is given by this equation here. So we want to predict the cricket chirp rate when the temperature is 82 degrees Fahrenheit. So we want to type the entire decimal here. So first you want to plug in, because we know that it says here degrees and chirps per minute. So it turns out that they're thinking that the temperature is going to impact the number of chirps per minute. And so therefore the temperature, in this case in Fahrenheit, is going to be your explanatory variable. So this is X. And then the chirps per minute is the response variable. So that's what responds to the change in temperature. And so if they provide you the temperature, you should be able to calculate the chirps per minute using this equation right here. So we're going to plug in for X. Like so, and in doing so you get the predicted chirp rate. So we'll go ahead and do that on the calculator here real quick. Type it in here. So we got negative 0.31. All right, and so your predicted chirp rate is 17.074. Okay, so we could just write it over here. Chirps per minute. All right, pretty straightforward. So you just want to be able to make that prediction using the equation, the regression line. Now using the same question here, but this time, or the same scenario, same regression line, but now we want to suppose the measured number of cricket chirps for a temperature of 90 degrees Fahrenheit is 16 chirps per minute. So for 90 degrees Fahrenheit, it's 16. Compute the residual for this temperature. So remember, to calculate the residual, you need to figure out what the predicted y value is for that particular point. So, and then you want to know the actual. So this is the actual minus the residual, or minus the predicted, I mean. So the residual is the actual minus the predicted value. And we know the actual value. The actual value is 16 chirps per minute. And to get the predicted value, you're going to have to plug in the temperature. So the temperature is 90, and so that's going to be X. So we'll do that right away. Okay, so go ahead and type that. So we got 18.77. So this is my predicted y value. And then when we subtract those two, we should get negative 2.77. And so the negative means that we over predicted here. So this is our residual. You type the entire decimal. Okay, and we'll double check that. And so my residual is negative 2.77. All right, the next one. The scatter plot shows the relationship between 40-yard dash time and the long jump distance in inches for a sample of students. The equation of the regression line relating these variables is y hat equals 415 minus 45.7x. So we want to be able to predict the long jump distance for a student who had a 40-yard dash time of 9 seconds. Type the entire decimal. So again, we're making a prediction here, and so we're going to be using the equation of the regression line. So we have here y hat equals 415 minus 45.7, and then we got to plug in for x to make that prediction. And so they're asking for a 40-yard dash time of 9 seconds. So that's going to be my x. So we have 9 seconds here. And we'll go ahead and calculate that. So we get 3.7. And then, so that's your long jump distance. So that's going to be in inches. So 3.7 inches. All right. Is this a prediction, an interpolation, or extrapolation? Type your answer. So this prediction is so basically what we did is we did it for 9 seconds. And so the 9 seconds, notice that 9 seconds is, this is 8, 8.5, and 9 seconds. So basically we had to extend past the data in order to make that prediction. And so therefore this prediction here is actually an extrapolation because we went outside the data set. If we were to do it within the data set, in the 5 and the 7.5, or the last data set that we have, because the latest data that we have is about 7.25, and the 5, and then about just a little bit after 5. So if we're within those two numbers, then that's an interpolation. However, we went outside. That's an extrapolation. So question 4, the equation of the regression line for the price of a vehicle given the number of miles that is driven is given by the following equation. In this equation, the y-intercept of, so we got to figure out what the y-intercept does. In this equation, remember that the equation of the regression line is y hat equals a plus bx. B is the slope. A is the y-intercept. So this example, the y-intercept is 38,257, and the slope is negative 0.1629. So the y-intercept is 38,257. And remember that the y-intercept only happens when x is equal to 0. So, which means x is the number of miles driven. Okay, so this indicates that so basically we're going to be talking about, x being 0. So the y-intercept being 38,257 indicates that the predicted price of a vehicle that has been driven, and in this case, x equals 0, right? What does 0 stand for? Well, x stands for the number of miles. So this is actually 0 miles. So the price of a vehicle that has been driven 0 miles, meaning it hasn't been driven at all, brand new, is $38,257. All right, using that same equation of the regression line for the vehicle, this time we want to predict the slope. So this is the slope right here, negative 0.1629. We can put that, we can think of that as being negative 0.1629 over an invisible 1. And the reason I do that is because, remember, slope is rise over run. And slope has to do with y on top and x on the bottom, right? We have to subtract y's, y2 minus y1, and then x2 minus x1. So the top is y, the bottom is x. This is like a quick review of algebra. But that means that the top value has to do with y, the bottom value has to do with x, okay? So basically, in this equation, the slope of negative 0.1629 indicates that the predicted price of the vehicle goes down because that's a negative. So it goes down by 0.1629. So basically, and this is in dollars, basically, a little over 16 cents, so it goes down by 16 cents with and a little extra for each additional 1 mile. The X stands for miles, remember, for each additional 1 mile. Or I guess you could say for each additional mile driven. All right. Given the eruption scatter plot and regression line below, estimate the residual for the point indicated in red. All right, so basically the residual here, if you look at this number, this red dot, remember the residual is y minus y hat. So the y is the actual data point, which is the point in red here that we're looking at. So it looks like it's about 90. That's the actual. And then the predicted y value, the y hat, is actually on the line itself. Okay, so you go down to the line, right there, and then you kind of guesstimate where you think it's at. So it kind of looks like it's around the 78 mark, you know, around there. It's not quite 80, but it's almost there. So we'll guess about 78. So, and this is an estimation. So this is going to be about 12. Maybe you can get away with saying 15 or something like that, or 10. So anywhere in the 10 to 15 range will be fine. And it's going to be positive. So looks like they got 12. So 12 is our answer here. Extrapolation is more inaccurate than interpolation due to making predictions outside of the data that was collected. That was true. So if you remember that if we were to go outside here, the data set, we end up going outside of our data, which is extrapolation. And extrapolation tends to be weak because there's not a really good way to predict, because what happens if, even though this data looks linear right now, what happens, we don't know that maybe after 7.5, the data starts looking like this, right? We're not sure about that. And if that's the case, then the data is no longer linear. It goes like this, right? It looks like a curve. So basically what I'm saying is that there's no way to know what's going to happen outside of your data set, because it could behave unpredictably. It could make a U-turn, right? Just like this. And so therefore extrapolations tend to be inaccurate. So this is actually true. All right, the scatter plot shows the relationship between the 40-yard dash time in seconds and the long jump distance for sample students. So this looks pretty similar to the equation that we did before. So one student had a 40-yard dash time of 7.17 seconds. And so that right here is, if they're saying one student had that time, this is the actual, data point, and a long jump distance of 65 inches. So this is our X, the 40-yard dash time is X, and the long jump distance is Y. We're thinking that the greater the faster you are, right, in the 40-yard dash, then the higher you jump, basically. And so we're thinking that that's the case. So in a long jump distance of 65, so that's Y. The calculated residual is negative 22.331 inches. Interpret this value. Okay, so we just want to interpret the value. All right, so the student had a long jump distance that was 22.331 inches. Now this right here, that negative, remember that negative indicates that we did an overestimation. That means that we overestimated the value, which means we estimated the value was greater than what it actually was. And so it's kind of opposite of what you would think, because remember, if the residual is y minus y hat, and this is your prediction, well, if y is 1, if the actual is 1, but you predicted it to be 3, well, then you over predicted, and so you're going to get a negative residual. 1 minus 3 is negative 2. All right, so we the long jump distance, that was 22.331 inches, less than expected. Or let's see here. Well, because we overestimated, right? Yeah, then it was actually less than what was predicted based on the regression line. All right. All right, and that is it for the lesson, guys. That is 2.5. I hope you took something from this video, and as usual, I'll see you in the next one.